Problem 27 may seem to have some weird wording to it, but you know what? That's really just a fancy way of saying the mean value theorem. That's what you're doing. You're finding the slope that's parallel to a secant line through those endpoints right there. So really, that's just a fancy way of saying, you're applying the mean value theorem. So calculate, we have square root of x, which is perfectly valid between 0 and 1, as far as, not undefined, or derivative certainly is okay. Meaning, differentiable everywhere in there. So f of 1 minus f of 0, you put 1 in there, square root of 1 happens to be 1, square root of 0 is 0, over 1 minus 0. So you have 1 over 1, which ends up being 1. So your secant line slope between those points on that graph would be actually 1. So you take the derivative of this function and set it equal to 1. So if it's x to the 1/2, the derivative would be 1/2 x to the negative 1/2. So for solving purposes, I like to rewrite that back as positive. Now, so you didn't see me do that really until over here, so it looks like something may be missing. But all I did was the x drops down to the bottom to become positive square root, and then, like I said, I used the c instead of the x. So, but you're fine if you just want to leave it as x. You're okay with that. So that's basically setting this equal to that slope right there, that 1 that we calculated from right here. So the derivative equal to 1. You have 1 over 2 square root of c. Cross multiply gives you 2 square root of c equals 1. Divide by 2 is 1/2. So to get from the square root of c to c, you square both sides, not square root, square. So basically, didn't write that step out, but so essentially just did this to both sides. And so 1/2 squared is 1/4. 1/4 is certainly in the interval 0 to 1. And like I said, we were guaranteed to get at least one answer for sure that fit in there. And it had to be in that interval. So the value where the tangent slope is parallel to the secant slope would be at 1/4. The c is basically your x. If you want to know the exact point on the graph, you can plug the 1/4 in, square root of 1/2. 1/4 is 1/2. So it's actually, the x value is 1/4, but the point would be 1/4, 1, 1/2. Decreasing. Well, kind of odd to ask just decreasing here, but I treat it as decreasing and increasing. You'd want to be aware of both. But we're going to take care of that here, so no problem. So we're looking for, now these kind of things, increasing and decreasing, you're looking for two things. Derivative equal to 0 for critical numbers, or the other definition of critical numbers where the derivative is undefined but the original function is not. That comes with those fractional exponents. That could also come with an absolute value function, which I usually don't ask, but mainly for derivative purposes. But the absolute value function certainly is going to have a critical number wherever the value that makes it 0, where it forms the V shape or upside down V shape. But anyway, you're looking primarily for the like x to the 1/3, x to the 2/3, stuff like that. Quotient rule: bottom derivative of the top minus the top x squared, derivative of the bottom's 2x over the bottom squared. Those do not cancel. Do not cancel. Now remember, we're only going to be setting this equal to 0. So we don't care about the bottom anyway. So you kind of work out that top part. You actually get a couple of 2x cubed terms, which I didn't write out and show, but they do cancel. So you really are just left with 4 times 2x, which is 8x on top. And so 0 is a critical number. So you're looking for two things: critical numbers and discontinuity. I talked about one of the other segments there that early on set of problems that, critical numbers and discontinuities aren't the same thing, but they both apply to this increasing, decreasing, and all the stuff we do with the graphing, because they both have their own effects on what's happening on the graph. So No discontinuities. So we have 0 as a critical number, so we break it up as 0. That means we have two intervals, negative infinity to 0, and 0 to infinity will be whether it increases or decreases. Pick a test value, something less than 0. I don't know why I chose negative 2, doesn't matter. Positive 2. And you plug it into the derivative. It's hard to see, but that's the sign of f prime. So you plug it into the derivative, a negative number, you plug negative 2, you plug that in there, it's going to be negative for sure, because you got positive on bottom, so it's negative over positive. So it's negative. You put positive 2 in there, you'll get positive. So when means negative means you'll have decreasing. Positive means you have increasing. So it's decreasing from negative infinity to 0 and increasing from 0 to positive infinity. So the original answer key probably only showed, I could check, but since it asked for decreasing, it only showed, I'm sure, decreasing, but you need to be aware of both. Yeah. Make that a little larger here. The 28, it shows the answer is negative infinity to 0, which is correct. But I would be surprised if you had a question that asked only for that, because you might as well ask both. So then it would have been increasing from 0 to infinity. Increasing, decreasing. All right, off the bat, we got a discontinuity. Kind of hand wrote this chart instead of, well, that seems kind of odd. Why do I have this and I have that down there? So that should probably be erased. Anyway, we got a discontinuity. 1 over x squared means you've got divided by 0 at 0. For sure. So let's move this up over here. Probably didn't need to do that, but it didn't hurt. Okie doke. So 0 discontinuity. So I take the derivative of this with the intention of looking for any critical numbers. So you take that derivative, you get negative 2x to negative 3. When you set that equal to 0, you get no way, nothing equals 0. And the other definition of critical numbers certainly doesn't apply here because it doesn't have a fractional exponent. So you have no critical numbers, but we still have to include that discontinuity. Now, when I teach this in class, and this is not that critical for the online students, but I will mention it just so you'll know why I've done this, and in case you've seen this in the notes and wondered. I will put it's not mandatory to do this if you're taking a paper and pencil test, and it's not mandatory to do it this way. But let me tell you why I do it. When it's a discontinuity, I like to put a dashed line in there because that way, when we get down here, and you'll see this here in a minute when we talk about relative mins and maxes, that way it may help you prevent from thinking, oh, increase to decrease, that's a relative max. But that dashed line indicates it's a discontinuity, so that can't happen in a discontinuity. You can't have relative extrema at a discontinuity. So that's kind of why I do that. But I never make that mandatory for students to do. But that would just be my little code word. Oh, okay. No relative extrema there. So you got, let's see, there we go. Increasing from negative infinity to 0, and then decreasing from 0 to infinity. I skipped over to put the test numbers in there. That's pretty easy. Put in negative 2, whatever, negative 1, cube, it's negative. Negative or negative is positive. So there's your plus. Put in any positive number there, you'll get a negative. So positive increase, negative decrease. Find the intervals, which is increasing and decreasing. Okay, this makes more sense. No discontinuities. That's an easy polynomial. This problem's real straightforward, I think. Take the derivative, 3x squared minus 6x. But I have seen people do some, on handwritten tests, some really scary and bizarre factoring, which makes me nervous about their algebra skills. But so anyway, factor out of 3x here. And that will leave x minus 2. Set those each equal to 0. 3x equals 0 means x equals 0. X minus 2 equals 0 means you'll get 2. So we have two critical numbers. I'll move that over here. We'll do this a little lower. And so that separates my sign chart into 3 intervals. Negative infinity to 0, 0 to 2, 2 to infinity. Pick test values. I chose negative 1. Between 0 and 2 is 1. Obviously, if you had consecutive integers there, you would have to use some sort of decimal number. But no problem. You're using a calculator to plug these in, so I don't think a decimal will be too troubling. Something greater than 2, I chose 3. Plug them into the derivative, sine of f prime. You get plus. When you put negative 1 in there, you'll get a negative number. When you put 1 in there, you'll get positive when you put 3 or anything larger than 2. So it goes positive, negative, positive. So we have increase, decrease, increase. All right, now we're finding relative extrema. So once again, I was just talking about this last one. You'd had a relative max at 0, f of 0, and a relative min at 2, f of 2. When I say f of 0, f of 2, that means plugging the value back into the original function. That's where students sometimes get confused, you know. Are we plugging something into the first derivative? Plugging something into the original function? You plug in your test points into the first derivative, that's it. But anytime that you want to know a point on the graph, that always gets plugged back in to the original function, because the original function is what defines the graph. So we have, let's look at this one, quotient rule. Bottom times the derivative of the top, which is 2, minus top times the derivative of the bottom would be 3 comes down, x plus 4 squared. Now I wrote the 1 here. Doesn't have to be there, but I wrote it there because I want to show you that I did not forget the chain rule. The derivative of the inside x plus 4 did equal 1. So, yeah, so I just want to show you I did include it, but obviously mathematically the 1 will go away. Then I have x plus 4 and then to the 6th. But then you see I just reduced all this to make it a little simpler in the numerator. It's basically the same thing if you factor out an x plus 4 squared. Everything goes down by 2. That cancels. This goes from 3 to 1. That goes from 6 to 4. Because we don't really care about the denominator anyway, but you want the numerator to be simplified. And that's, yeah, to set this equal to 0, we got to get this thing numerator as easy as possible. So what do we have? We have, so then that goes to the first power, which then allows us to distribute. So you have 2x plus 8. And over here, all you have left is a 2x and a 3. So you have 2x plus 8 minus 6, 8. 8 minus 4x, set that over the x plus 4 to the fourth. Set that equal to 0. And like I said, we don't care about the numerator. I'm sorry, we don't care about the denominator. We only care about the numerator. So set the numerator equal to 0 and you will get 2. But notice up here I wrote off to the side, I was going to go back now and explain that, is you look right at it, it's real easy to pinpoint visually that you certainly have a discontinuity at -4. So had we not even gotten any critical numbers, we absolutely would have put -4 on our sign chart. No question. All discontinuities and all critical numbers, if any, apply. And so we have -4 on there, and once again, there's my little dash line trick there, it's not that critical. And I put 2 right over there, a critical number. And went through the sign chart process. So you see I've got my 3 intervals, picked my test points. I didn't show these plugged anywhere, but anyway, you can plug these into the derivative. Obviously, you could use a T-chart. the calculator chart to do it. No problem. Table, whatever they call it. But this one, if you look at this, if you here's a simplified derivative 8 minus 4x over x plus 4 to the fourth. Well, obviously you're not plugging in negative 4 for any reason, but any other number you plug into that denominator is going to be positive because it's raised to the fourth power. So really, whatever the sign of the numerator is, if that's positive, the whole thing's positive. If it's negative, the whole thing's negative. If you put negative 5 in there, you're going to get positive on top. If you put 0 in there, you're also going to get positive. But if you put something bigger than 2, like 3, you'll get 8 minus 12, which is negative. Positive, positive, negative. So our function goes increase, increase, decrease. And we do have a relative min at 2f of 2 because we're changing. Oh, no we don't. Good grief. We have a relative max at 2f of 2. Change the color here. Wow, I don't know how that got through there. I'm surprised that hasn't been brought to my attention before. Unless it has and I forgot to change it. Now I'm going to have to move this over a little bit. Well, not that. I'm going to try to write the word max again here the best I can here with this thing. Well, that's not too terrible, but it's a relative max, not min, because it goes, anytime you're going from increase to decrease, that is a maximum. Now, once again, even though this did not change, increase, increase, but had it changed, either increase, decrease, or decrease, increase, negative 4 cannot be a relative min or max because it is not a valid, it's a discontinuity. It's not even on the graph to begin with. So, yeah, you see the answer on the thing here is right, relative max. So yes, it's a relative max. So sorry about that. 32. Find all relative extrema. All right, another polynomial. This is pretty straightforward. Easy derivative. Set that equal to 0. Nice and factorable. And of course, you can get that. That I think what makes that a little easier is you can pull a 6 out of there. Makes that factoring easier. So you have x plus 2 and x minus 1, which gives you negative 2 and positive 1. So those are the values going on our sign chart. Obviously, there's no discontinuities. So pretty straightforward. Pick your test values. I use negative 3, 0, and 2. Plug these into the derivative and see if they're positive or negative. I got plus, minus, plus, which then leads increasing, decreasing, increasing. Hadn't been asking for that. And then increase to decrease, relative max, negative 2, f of negative 2. And relative min, decrease, increase, 1 comma f of 1. Now, and if you had to get the actual y value, if that was necessary, it would not be that difficult then, especially with the calculators. Take those x values and plug them back into the original function, remember, not the derivative. That's what I was mentioning in one of the other videos, that sometimes people will put these back into the derivative and they keep getting 0 for the y value. So if the derivative set equal to 0 and you plug them into that derivative, those numbers, of course, are going to give you 0. So, but they still can give you 0 anyway, and you can still have a critical number be on the y-axis and x-axis. That's fine. You could have where a graph, maybe did something like this, dip down, and then here's well, it's a pretty sorry looking x-axis there, but you see the value, y value, not only would the derivative there be 0, critical number, the y value would also be 0 because it's sitting there on the x-axis. But point being, though, you still plug them into the original function. Let's see. Okay, so you got a relative max at x equals 6. That means your function would have gone increasing and decreasing, and that means the first derivative would have been positive up before 6. I just kind of drew that right here to indicate the slopes. Positive going up before 6, down. So that would have made it positive before 6, negative after 6. So clearly that's the correct statement. F prime is negative on the interval from 6 to infinity. Now, this is under the assumption that there are no other critical values, which there aren't. So you can take that as an assumption, like, what if 10 would have been a critical number? Then would have been from 6 to 10. But anyway, they're not trying to trick you with something like that. So, but yes, it would have. The interval would have stopped at the next either critical number or discontinuity had there been one. But you see, that's not even an effect on any of the answer choices, so no problem there. Okay, first derivative test, relative extrema, same thing. This is a pretty straightforward polynomial. Probably shouldn't be too difficult. So derivative, negative 4x cubed plus 6x squared. I factored out a 2x squared to get negative 2x plus 3. Gives me 0 and 3 halves when I set those each equal to 0. No discontinuities, of course. So it breaks down, you have 0 and you have 3 halves, so you create 3 intervals. Pick test points. I use negative 1. I use positive 1. I use 2. Those aren't the only ones. Plug those into the derivative. You can use the factored form of the derivative if you want. In fact, if you notice this, you don't have to notice this, but if you notice that 2x squared would always be positive. So positive has no effect on multiplication, so only negative does. So then you really all have to do is plug it into the negative 2x plus 3. Because then as soon as if it's positive, and then times positive, still positive. And then negative times positive is negative. So that's okay, though. You can just plug it straight in the calculator. You don't have to use little tricks like that. Plus, plus, minus. So you have increase, increase, decrease. So you only have one relative extrema there, the relative max, where it goes from increase to decrease at 3 halves, f of 3 halves, which once again, if you actually needed to know the y value, you could plug it back into the original function, if need be, using a calculator, no problem. You don't have to do that manually. Well, this question is a little bizarre because it's not indicating what it... Oh, this problem was probably supposed to be multiple choice. And if I could find the original file here, let's see. Let me see if I can open this up real quick and find it. Well, that's coming up. You see, I took the derivative. We found one critical number at negative 2. The sign didn't change. So that's the reason why it's not any kind of min or max. In other words, it goes increase to increase. But obviously, in this particular problem, the result's not the issue. Is you couldn't tell what the question was asking. I guess that might be a problem. I'm going to see if I can change the mode on this. Question type. Oh, it is bimodal already. Oh, yeah, there it was. Huh. Well, let me go ahead and copy this. Well, lots of places it needs to be put now, but at least just for the time being, I don't want to waste a lot of time with this. So let me completely get rid of what I had up here. So obviously this needs to go to the original file too. And then the PDF. And then this. But I'll put it here right now. So I need to make a little room here. Just to cover that. Alright, move this around here. But anyway, the work below it's good. See, I took the derivative. Like I said, we know that it's not any kind of, negative 2 is a critical number, but it will not be any kind of a extreme being relative inner max. I should be able to put this right on top of that and hide the other one. All right, there we go. Good grief, there we go. Well, obviously that now needs to be fixed in a couple other places. Critical point, but not an extremum. I don't think that was right. There's no way it could be right here. I'll check, but I mean, right isn't. Yeah, it is. We saw it. Okay. There we go. So that fixes that one up. Because that was kind of confusing on what it was asking. I can see why. This one just is asking us to show that it's increasing. Probably not the kind of question that I would ask on a test, but it's certainly good to look at to see why, to know. So let me just explain this real quick. Just take the quotient rule, and I won't go through that, but simplifies to 1 over 1 minus x squared. Now notice it says wherever it's defined. It's not defined at 1. So anywhere outside of 1, so in other words, from negative infinity to 1, parentheses, and then parentheses from 1 to infinity. So, but if you look, the reason why, how do we know? Is because look at that 1 over 1 minus x squared. Well, as long as you don't put 1 in there, anything in that denominator is positive because you're squaring it, and you already have a positive 1 on top, so you have positive over positive. So the derivative is positive everywhere. So if the first derivative is positive, that means increasing. Okay. I thought that was kind of interesting just to take a look at and sort of understand why that was the case. But obviously, you could have used, if you were doing it more formally, we could have put the discontinuity on there, no critical numbers. We could have plugged in your test values, and you would have come to that conclusion same way. You could have got positive, positive, but just sort of a shortcut way, just say that's going to be positive everywhere, except 1. Same problem? Yeah. I guess these two could have been combined in the same problem. No critical numbers. Because you set that derivative equal to 0, you'd be trying to set the numerator equal to 0. Well, 1 equals 0, that's kind of a contradiction, correct? So there's no variable there, so 1's not ever going to be 0. No critical numbers. What do we have here? Let's see. Critical number at negative 3. Identify the relative extrema if you know that the derivative of negative 4 is positive 1/2, and if you know the derivative of negative 2 is negative 1. Now, I didn't do our big fancy, normal sign change chart. I just did a little number line deal here, where here's our -3 that we're trying to check if it's a min or a max. We know there's a critical number. So the positive actually indicates the derivative sign here. So I'll put that in red and see if I can make a look at that. That's sort of the way I used to do these kind of charts a few years ago. But I like the way that they organize it in the textbook, so I decided to go ahead and start doing them that way. With the box and everything. So there we have, so you know that because it tells us that f prime of -4 is 1/2, therefore you assume everything below -3 is 1/2, is positive. And then the fact is the derivative of -2 is -1. See, those would have been like test values that I have circled there. So at -4, it was positive. At -2, it was negative. So it's going up to down. So that's relative extrema means we absolutely have a relative max there at -3, 3. Okay. You might have just looked at that and looked at the positive and negative and figured that out without having to write that out. And that's certainly fine too. 39. Now we're getting into concavity, which involves a second derivative. I don't like these to get too rude, for the second derivative because it can get kind of ugly. And this one has a quotient rule, but actually you'll see that the first derivative tidies up pretty nicely. That's the only reason I put a problem like this on here. All right, so you have x plus 3, bottom derivative of the top is 1, minus top times the derivative of the bottom, x minus 1 over the bottom squared. So that numerator ends up tidying up to where, now I kind of skipped a step here. The step I skipped was it's 4 divided by x plus 3 squared, which I just lifted that up and made it negative, because you may recall in another problem earlier, possibly in one of the other segments, it might not have been this one, but I said when I have a number over a variable term, I generally bring it up and just do the general power rule for the derivative chain rule instead of quotient rule. So I basically lifted that up, and then the rest of that simplifies into 4. And take the derivative, -2 times 4 is -8. And makes it x plus 3 to the -3. You've got to do the chain rule. The derivative of the inside is 1. I want to at least write that there to show that I didn't forget it. My statement's correct here about no values where the second derivative equals 0. Maybe I could have written an extra step here where I would have, y prime, double prime. So all I left out was this. Maybe that would have been easier for you to visually see. So once again, the same thing, you're setting the numerator equal to 0. So -8 cannot be 0 ever. So there's no values that could ever possibly be what's called inflection points. So that can't happen. So, but we do have that discontinuity, right? See that bottom, so we've got something that goes on our chart. So just like the first derivative, we're looking for the second derivative equals 0, second derivative undefined, but the f of the number is defined, and discontinuities. So all we have here is a discontinuity. So -3, I use my little dash trick there, but this one was not asking for inflection points anyway. So test value, I chose -4 to the left of -3. I chose 0 to the right. Put it into the second derivative. You're going to get positive when you put that -4 into the second derivative, and you're going to get negative when you put it into the second derivative. So positive means concave up, negative means concave down. So you're concave up from -infinity to -3, and you're concave down from -3 to +infinity.